Today let's solve the search insert position problem together, and for this problem, let's go through the description first. So we are given a nums array which contains integers, and we are also given a target which is an integer. And our goal is to find out the position that target should be in nums. There are several different situations, and I have concluded here. The first situation is that target is in nums. For example, nums equal to 1, 3, 5, 6, and target equal to 5. In this case, we will return 2, which is the exact position of target here. The second case is that target not in nums, and this situation contains several sub-situations. The first sub-case is that target is less than nums 0. So in this case, we will just return 0. The second case is that target is larger than nums minus 1, and in this case, we will return length of nums. And the third case is that the target is larger than nums 0 and less than nums minus 1. And in this case, we will return the position that target should be. For example, in this example, 2. 2 is larger than 1 and it's less than 3. So if we insert 2 into nums, we will put it in the position of index 1. And we will return 1. I will use binary search to solve this problem since the array is sorted, and for the target, if we would like to insert the target into nums, we will know that all of the elements before target will be less than target, and all of the elements after target will be larger than target. There will not be any duplicate values sorted in there will not be any duplicate values in nums. So the position of the target will be unique. So let's use binary search now. I will have left equal to 0, and I will have a r equal to length of nums. And why I would like to let r equal to length of nums, it is because the position of target might be the length of nums if target is larger than nums minus 1. And I will have a while loop here. And in the while loop, when we determine the range of target, we will assume that the target is inside left, is inside the range of left and right, and on both sides the range is inclusive. So let's have mid initialized here. So mid is equal to L plus R minus L over 2. And then let's have several if statements here. If target is larger than nums mid, left will be equal to mid. So, for example, actually left will be equal to mid plus 1. For example, in this case, if mid equal to 0 and target equal to 2, we will know that nums mid is less than nums target, and then we will ignore all of the elements on the left side of 0 as well as the position 0, because we will know that if we insert target into nums, the position of the target will never be 0, since nums mid is less than target. And then if target is less than nums mid, right will equal to mid. Because we will know that, for example, in this case, if we compare position 1 and target, position 1, nums 1 is larger than target, and in this case, we will know that these elements on the right hand side of nums 1 will always be larger than target, and the position of target will never be these positions here, but the position of target might be the position of 1 here. So we let R equal to mid instead of mid minus 1. And finally, if target equal to nums mid, we will just return mid. And that's it for the while loop. And after the while loop, we will return left. Since if we go out of the while loop, now we will have left equal to R, and at this time, L and R are the only position that the target can be. So we just return L or R. Let's run together. It is accepted, and let's submit. It is a quite efficient algorithm, and the time complexity will be O log n, since we remove half of the elements every time in the iteration. And the time complexity will be O1, since we do not use any extra space here. And that's the solution for the problem. Thank you.